I do now. If you want to come over to this, I'm not on the.
Okay, can we come back to numerical differentiation? I know your project is very exciting, but later. Thank you. Can we please come back to the class and have the discussions later? So we are walking through numerical differentiation. Numerical differentiation. This is chapter 23 in the textbook. It's part of our module 4. I told you in the exam there will be exam 2 will have one question of what we consider average difficulty on this topic. Okay. So last lecture we talked about how if we have a bunch of data, how would we calculate the first derivative? So if this is y of x and this is x, you are presented data in a tabular form, x1, x2, x3, xi, let's say I plus 1, I minus 1. We looked into how to compute dy over dx at a point x equal to xi, or d squared y over dx squared at that point, at a specific point, and so on, using data as xy pairs. This is what we started seeing last time. And we saw a couple of formulas. So for the first derivative or the slope, dy by dx at x equal to xi, we saw what is called as the forward difference. Clue, it involves I and I plus 1, or the central difference, which involves the current point I, the forward neighbor I plus 1, and the backward neighbor I minus 1. And we also saw the backward difference approximation, which involves the current point and the backward neighbor, or the leftward neighbor. Forward difference, first order accuracy, we have dy by dx equal to yi plus 1 minus yi divided by delta x plus an order of error, that is to the order of delta x, that is the error of truncating higher order terms scales with delta x. That's the implication of this symbol. Just recapping what was discussed last time. And then central difference, second order accuracy. Dy by dx equal to yi plus 1 minus yi minus 1 divided by 2 delta x plus order of error scaling with delta x squared. And then backward difference, again first order accuracy. Dy by dx equal to yi minus yi minus 1 over delta x plus order of error of delta x. This is for approximations for the slope at a point. Without going over it again, these formulas are obtained by starting with Taylor series for yi plus 1, yi minus 1, yi plus 2, yi minus 2, and so on, as a perturbation of yi and derivatives at x equal to xi. That is yi is nothing but yi is the value of y at xi and its derivatives at xi. So for example, yi plus 1 is yi plus delta x times dy by dx at xi plus delta x squared over 2 factorial times curvature at xi plus delta x cubed over 3 factorial times the third derivative at xi plus and so on up to infinity. This is the only one equation that you need to remember or know. If you know this conceptually, you can then set up the same equation for yi minus 1 or I plus 2 or I minus 2. If you understand the grid, that is, if you have xi plus 1 is nothing but xi plus delta x, I plus 2 is xi plus 2 delta x, and xi minus 1 is xi minus delta x, and xi minus 2 is xi minus 2 delta x. If you understand this gridding, you can tie that with this Taylor series, and if you understand this, you can derive all those formulas whenever you need them. So you don't want to turn this deriving this formula into a memory exercise. You can derive them if you understand the principle. I'll give you a time to catch up. Whether you look at your notes or you look at figure 23.1, figure 23.2, actually put it here. Forward difference formulas can be found from figure 23.1. Backward from 23.2, figure 23.2. And central from figure 23.3. Whether you derive it yourself or you look up the text to get these formulas, once you have the formula, you can compute derivatives or slope, curvature, and so on. So here is a simple exercise that we can do. Refer to these figures from the text, and write down for me the forward difference, central difference, and backward difference formulas for the second derivative. That is, fill out this table, but for the second derivative. So just use the figure 23 as a lookup table. I want the curvature or the second derivative at x equal to xi. Central, I'll start with forward, central, and backward. Can you look up and write it? Do you have your text with you? please go to page 656 and 657. What you need is already on there. So the exam template will be something like this. You will be given figure 23. Will be given, and you may have to compute a derivative using a table of data. So what you may have to decide, or the decisions you have to make, are central, forward, or backward, which formula to use, and order of accuracy. These are the two decisions that you have to make. So I'm asking you to get me the approximations for the second derivative using forward, central, and backward differencing. Look at figure 23 and fill it out for me. I won't ask you derivations in the exam. I want to ask you to get me a fourth order approximation for the fifth derivative, nothing like that. Can somebody look up and just read it for me, or whatever you have on your notebook?
Central.
Yeah, central.
The numerator, it's y plus 1 minus 2 times y to I plus y minus 1 over delta x squared.
Thank you. And this is accurate to what order?
Second.
This is accurate to second order, or accurate delta x squared. Thank you. So he got the one for central. Can anybody look up and tell me the approximation for the forward and backward? So the forward approximation would be yi plus 2 minus 2yi plus 1 plus yi divided by delta x squared. And this order of accuracy is to the order of delta h or delta x. First order accuracy. And this one is yi minus 2yi plus 1 plus yi minus 2 divided by delta x squared plus order of accuracy delta x.
Question.
Yeah,
Backwards difference.
yeah.
Are we using I plus 1 and I minus 2?
1 second. Backward differencing I minus 2. Sorry, this must be I minus 1. Yes,
Oh, okay.
656. Page 656. So I hope many of you are carrying your laptop and Excel with you. I post this on. Give me 1 second here. I'm going to post a file on Canvas. You can download that and we'll continue the problem. Okay. Okay, so if you are on Canvas, please go online now and check for module 4 class version. Okay, I'll show you the file. Please download that file and we'll continue now. So I want you to grab this file. Which one? Yeah, this one. Module 4 class version. Can you grab that file, download it to your computer, and then we'll start or we'll continue. Okay. It will have this file name class version. Look for it. MECH 3341 module 4 class version. And if you open it, you should see this page. If you confirm that you have downloaded and ready to go, we can continue on. Good. Now 3:05 p.m. It's on the root folder. Are people who are going to do this with me ready? Yes. Okay. So let's go to sheet 5. Okay, go to sheet 5. Follow with me, sheet 5. Okay. So if you see here, column E and F, I have what is labeled as y of x raw. Okay. So just you already have the file. There is nothing to catch up here. We are starting at the same point. So look up. So you have y of x raw and then x value. So if you scroll a little bit to your right, you can see y of x raw and then y fit and then y of x smooth. Just look at the left hand side plot. Y of x raw. This is the data. It is just the one that you have presented. We plotted it. And then there is a bunch of noise here because of the way the data is. We did do a fitting. That's part of your participation exercise. So we did the fitting. So I assume you know how this curve comes about. For everyone, is that a fair assumption? That you know how this curve is derived and you can plot it along with. Now, if you just scroll down to the left, okay, just scroll down and look at this plot here. This is dy by dx calculated using the central differencing approximation based on the raw data. Answer some questions for me. If you look at this dy by dx plot between, let's say, 0 to 1, that is between here and here, what can you tell just by looking at this cluster of points here? What will you tell if only those points are presented to you? Is there any discernible trend? Can you say it has any particular value? It looks like random scatter, right? But if you scroll up a little and you look at the data between 0 to 0.5, and I ask you what should be the slope of this data, what will be your response be? It should be negative. It should be it looks like almost like a straight line between 0 to 0.5. So it should be something of a constant slope, maybe with some noise. But what you see here is almost, you can't interpret anything between 0 to 0.5. Do you see that contradiction first? What you think must be the slope, some negative number isn't seen here. So first, how do we get here? That's the question. Before to answer that question, why is this happening? That is, you take noisy data and you do a difference. What happens? Why are you getting this random scatter? Okay, I'll give you another clue to answer that. If I ask you to compute the area under the curve between 0 to 0.5 using trapezoidal rule, how will you set it up? You know how to do trapezoidal rule. You'll take the first point and the intermediate points in the last point, and you'll get the value. Shall we do that first? What I'm saying is, based on the data provided, I want to compute integral y of x dx over the range of the data. So that would be, if I go here, oh, not this one, sorry. I want to do weightage factor. I'll call it W of x. For the first point, the weight is 1, and then remaining points it's 2, except for the last point where it's 1 again. And then I have W of x times y of x. So I have W of x times y of x raw. So I'll do that. Okay. Oops. And then what I'm going to do is to write sum, which is sum of this column. And what is my delta x? Delta x value can be the sum of difference between any two rows minus this. And what is the number of segments? I have 352 points. So what is the number of segments? Number of segments is the number of points minus 1 plus 2. 352 segments. No, is that correct? No. Minus 2 plus 1. 350 segments. So my I numerical is half delta x times the sum. So this is my integral based on the noisy data. You don't have to do all of this necessarily, because I will save this file and repost it. But I want you to at least keep up with me. What did I do here? I calculated the area under the curve for the raw noisy data. That comes out to be 3.85 something. Okay. Now the clue is, what about addition kind of diminishes the effect of noise, and what about subtraction or differentiation or difference amplifies noise? That's my question for you. Why does noise get squished when you add up things, when you average things? Why does noise get amplified when you do subtraction? What happens when you do addition? You have not, what is noise? Random fluctuation, right? Positive values, negative values. When you do addition, those out of phase values cancel each other. Like you have a positive 5 and a negative 5, they add up and you get 0. So the noise gets diminished when you do addition. That's what integration represents. But when you do subtraction or difference values, sometimes small values or small differences basically double. So you have 5 minus 5 gets you 10 now instead of 5. In addition, it becomes 0. In subtraction, it becomes double, like 10. Okay. So whenever you have noise, the noise basically increases the level of randomness or noise. The differentiation operation increases the level of noise that you can't see anything out of this. But what is your expectation? What do you hope to see? Or what do you hope to see as the slope? Some negative number, right? That's what the slope or the geometry suggests. So how do we get there? So step one, we create. So this is where you, if you have the Excel file in front of you, take a moment, go to column J and check out what the formula looks like for column J. Go over it line by line and see what I have done. When I click that first line and I say average of 25 numbers, and then second line, I say average of the next 25 numbers, and then third line, I do average of 25 numbers, and fourth line, I do average of 25 numbers. What am I doing here? So if you look at the plot, this is the raw data, okay? The raw data looks like on the left, the smooth data looks, it captures all the geometry, but all the noise is now gone. And I did that by taking a rolling average of 25 numbers. So that is, at every point I did a smoothing wherein I took that point and I took the next 24 points and I took a rolling average of those next 25 numbers, because I know the noise will keep going up and down, but the trend will be continuous. So I did this average and I did this again and again, so that then I got this column J, which is y of x smooth. We'll call it smooth. Okay, we did some filtering. So take a moment, go through column J, see what I have done. Tell me you're okay with it, then I'll tell the next. It's just a rolling average. It's like first 25, 2 to 26, 3 to 27, 4 to 28, and so on. That stencil of 25 numbers keeps shifting to the right. Yes. I found that by trial and error. I tried 4, 10, 15, 20. I thought 25 gave me a nice smooth curve. It's just by trial and error. 25 has no particular significance. It could be 20 also. Good question. Are we okay?
How does that hold up at the end of the data set? Because you just start averaging the end of the data with zeros as blank cells.
In Excel, blank cell is counted as a non-entry, meaning you took, if you had only 10 and 15 empty cells, the denominator automatically becomes 10. So it's an average of last 10 or last 24 numbers. Are we good? Okay, so now what I want you to do is delete whatever is in column K and L, and let's do it together. Delete column K and L, the ones I had in there. Let's start over. Okay, so column K, I want us to compute the slope using the central difference formula that is based on the raw data. You're ready? So what you do is yi plus 1. We'll leave out the first entry. Okay, we'll start with the second. We want yi plus 1 minus I should start with the second row. Yi plus 1 minus yi divided by 2 divided by delta x being 0.01. Can you compute this, and let's all agree if we are getting the same number before we proceed? Are we getting this minus 5.96? So the formula I used is dy by dx equal to yi plus 1 minus yi minus 1 divided by 2 delta x. Use this formula and see if you get minus 5.9643. Are we all getting this? Those who are trying? Yeah, you're getting medicine. Yes? Not getting? So let me try again. Do it with me. So you are here. yi plus 1 is entry I4 minus yi minus 1 is entry I2 divided by 2 divided by dx, which I've already stored here, or you can also do xi, sorry, yeah, you can do xi plus 2, sorry, xi plus 1 minus xi minus 1. That will also give you this. So you alternate way of doing this is yi plus 1 minus yi minus 1 divided by xi plus 1 minus xi minus. Come again? So we have to do for many rows to before coming to any conclusion. I just want to make sure all of us are getting this number minus 5.9. Yes.
How about the first row? When your I is.
You tell me. You at this point you and I know the same amount of information. So you tell me. See, first point you can't do central. You can't do backward. That leaves only one option. Forward. That's all. Are we good? So once you are here, then just drag it down all the way to the bottom so that you get a bunch of entries going into the last row, except you can't use the same formula for the last row. For the last row, you can't do central, you can't do forward, which leaves what? Backward. So for the first row, you use a forward difference formula, yi plus 1 minus yi divided by xi plus 1 minus xi. For the last row, you use yi minus yi minus 1 divided by xi minus xi minus 1. So please do that. Xi, yeah, here, yi. Okay, so first row value you should get something like 14.7478. The second row should be minus 5.9642, and last row value should be minus 0.7499. Make sure you are getting these 3 points, which means we'll get everything else too. Okay. Yes. You need to be a little louder. It's very hard to follow. Yeah, Radhe. Okay. So once you have filled out column K, move over to the right and look at this plot. It looks the one on the left. That is the second row left plot. It's the one that is super noisy, doesn't give you any conclusion. You can't say the slope is negative or positive. It's just all over the place. It's not a very useful calculation. Now what we do is we go back to the data, look at column L, do the same operations, except now use the smooth data and not the raw data. Use the smooth data to do the same operation. Let's make sure we get it right. So you should still use the X values and Y smooth instead of Y raw. Same formula, just the data is being swapped. Okay. So this is for raw. And for smooth, for the first point, for the last point, you should get minus 0.3749. For the second point or the second row, you should get minus 3.0966. For the first row, you should get minus 3.1260. Yes. For the smooth or raw?
For the raw.
Okay.
Yeah.
For the raw.
I'm getting like -0.7.
Okay, I exactly don't know what's happening in your sheet, but are you having these two columns, the X and Y raw? So when you want to calculate the derivative based on that, you just make sure that it's a difference between consecutive rows for the first row, and for any of the middle entries, skip that current row, go one step forward and one step backward. So look at this cell here. I'm not able to magnify it more, but look at this. Did you also include a 2?
Yeah, I think it's because you're.
I did the second version of the formula, but you might have included a 2. So remove that 2, you should get it. Are you able to get the derivative using both raw data and smooth data? All of you or some of you? Yeah. Okay. If you have this smooth data derivative calculated, go over to the plots and now look at the plot in the second row to the right. Second row to the right. Remove this function. We can bring it back later. But look at this plot. Okay. So the question is, if you look at the right column, that is the right hand column, y of x smooth, and then the slope based on central derivative based on the smooth data, do you think this makes a little more sense? Why does it make more sense than to the plot on the left? Sorry? Why does it make sense? Why is this more looking correct than the one on the left?
Change.
Sorry?
Follows the slow change.
So if you look at the top plot here on the data, you should get a negative slope. Look up, please. You should get negative slope here between 0 to 0.5. That's an expectation which you can check by scrolling down. Look at between 0 to 0.5. Do you have a negative slope? Right? So here, over here. So look at this. Do you have a negative slope here? Yes, no? Okay. I think I'm running in circles here. Okay, please look up. I have different people look up at different times and kind of not following this, but let's try again. Look at the top plot over this one where my mouse pointer is. Between 0 to 0.5, what is the slope here? Is it negative or positive? Negative. If you look at the bottom plot, okay, the bottom plot is not the data, it's the slope of the data, and you expect to see a negative number or a positive number between 0 to 0.5. Negative number. And that's what we are seeing here. Look at my mouse pointer. We are seeing a number which is negative. The slope is decreasing, and then the slope goes to 0. Does that match the data here? The slope is decreasing and then goes to 0. Okay. So if you consider the top data to be your raw data, there the slope is negative initially, then the slope decreases and then goes to 0. You can see that happening in the bottom plot where the slope is initially -3. It gradually becomes lesser and lesser, goes to -1, 0, and reaches about 0 and then starts to peak there and then starts coming down again. It matches exactly with what you would see here. So between 1 and 2, what is the nature of the slope in your raw data, in your smooth data? Between 1 and 2, is the slope negative or positive? Negative. Between 1 and 2, your slope calculated becomes negative, reaches a minimum, and then comes back again, but it remains negative throughout the entire time. If you compute derivatives, either first derivative, second derivative, or anything, if it can't explain the geometric features in your data, it is a useless calculation. That is what I'm trying to advance here. If this is your raw data, anything that you compute as slope or curvature should explain the features in this, in these valleys and mountains and everything. Okay. What prevented us from doing it on the raw data? If you just took the raw data without smoothing, you got a bunch of noise. Do you realize that without smoothing, this calculation leads you nowhere? Okay. And then if you repeat this for second derivative, the noise gets worse. So previously, if the noise level is, look at this data set. If you have values around 2, they fluctuate between 2.1 and 2.2, or fluctuate between 2.3 and 2.1. The fluctuation level, which can be taken like approximately 0.2 or 0.1, what's the level of fluctuations in the slope? Look at the numbers and tell me. What's the y-axis spread here? It varies between -15 to +15. So what was previously 2.1 unit is now 10 units, or your noise level has gone up by 100 times, 10 over 0.1. And if you compute the second derivative, it's now reaching levels of 150. So your noise level is now multiplied by another factor of 10. It's exponentially increasing. So what is the inference from all this? What should you do whenever you get a table of data and you are going to use that data for calculating higher order derivatives? What is the first thing you should try to do? So when does a data required to be smooth? Like, should you smoothen out every data set, or is there any condition you should think of before doing that?
Well, looking at the part of the first derivative.
The thumb rule that I would give you is, whenever you are going to do differentiation, be very, very aware of noise, because differentiation exponentially multiplies noise. That's what you saw here between the raw data and the first derivative and the second derivative. The noise just keeps increasing by a factor of 10 in each step. Okay, so can you tell me one famous application where you take data and then use it to compute first derivative quantity that has some physical meaning, and then a second derivative quantity that has even more important physical meaning? Position, velocity, acceleration. Our friends that have been with us since high school, right? So some of you, I don't know if any of you are doing such experiments. If you are using a camera to record position, and then from the position you want to calculate velocity and then acceleration, if you have noise in your position data, you are screwed. Screwed in the sense your noise will only get worse as you compute speed and acceleration. Suppose, here is the engineering question. You can do an experiment in two ways, okay? You have a speedometer in your car, right? It records speed, okay? Let's say you have a logger that gets you V of t for your drive from school to home. For the time you take from go to school to home, you have a logger which for every, let's say every 30 seconds, it records the speed that you are at based on whatever the instantaneous speed of your speedometer is, it just records. Okay, so it gets you a bunch of curves. Something. There are two quantities that you can compute here. One is, I want to know what is the distance to your house. How will we do that? How to compute distance if you know the instantaneous speed as a function of time? That would be integral 0 to t v of t dt. This is your trapezoidal rule. Okay. Then I also want to know if this is your speed data, I want to know what is your acceleration as a function of time. Okay, that is, let's say you have something like this. Based on the speed data, and if I know a little bit of math, I can tell you how good or bad your driving is. What's happening here in this graph? All these periods where you had an intense change in speed is either you accelerating from a stop sign or a light, or you coming to rest, screeching your brakes and coming to rest. All of that information is in here. Okay, so how will we get acceleration? We will get this as derivative, that is v I plus 1 minus vi divided by delta t. Okay, is this the only way this measurement can be done? Can you think of other ways of, we need three pieces of information. We want the distance, we want speed, we want acceleration. One second. Option 1, I choose to read out the speed from the speedometer, go one direction to get the distance and other direction to get acceleration. What other ways can you imagine the same measurement? Yes. Okay. So she wants to use an accelerometer, log that data. So let's say we have the accelerometer data. It gives you instantaneous acceleration. So when you're starting off, it increases. So your initial acceleration is high, and then your acceleration may top off and then it may reach 0. It means, let's say you reach the freeway, and then in the freeway you are maintaining 55. So the accelerometer data will keep reading 0 because you're not accelerating. And then it may then come back, and then you may enter the exit, and then you have to decelerate, and you're entering your neighborhood, and then you finally come to rest, something like that. So with this data, if I want speed, what do? I have to integrate v of t dt. And if I want distance, I would have to integrate the speed, which itself is an integral. So you'll have to do some kind of mapping, time-dependent mapping. I can go into the details, but that's not the point. The other way of doing this measurement, there is a third way we can think of. One involves speedometer, one involves accelerometer. What else can we measure and get the other two? Position. Let's say we take data from your GPS and we want to plot distance versus time, or position versus time, XY coordinates versus time, and you have something here. To get velocity, what will you do? Differentiation. To get acceleration, you will have to differentiate velocity. So which method will give you maximum chance for noise multiplication, and which one gets you maximum or minimizes noise overall? Differentiation exponentially multiplies noise. If you had noise in your distance data, that will get 10x amplified when you compute velocity. That will get 10x amplified when you compute acceleration. Because subtraction multiplies or increases the noise. This one, the accelerometer, gets you directly acceleration. So you integrate twice. Integration operation always suppresses or smooths out noise because it's an addition operation. The middle path, measuring speed and going one way up and one way down, again, it's the middle path. It gives you best or worst of both worlds. Okay. So coming back to our situation, I want you to try this. Take this second derivative on the raw and smooth, delete this numbers, whatever I had in there, and recalculate those numbers for the second derivative based on raw data and smooth data. Go ahead. So we are doing second derivative using central differencing. D squared y over dx squared equal to yi plus 1 minus 2yi plus yi minus 1 divided by delta x squared. This is for rows 2 to 2 to n minus 1. For the first row, we'll do d squared y over dx squared equal to yi minus 2 yi plus 1 plus yi, hold on. Actually, forward derivative y I plus 2 minus 2yi plus 1 plus yi divided by delta x squared. For the last row, d squared y over dx squared equal to yi minus 2yi minus 1 plus yi minus 2 divided by delta x squared. So please use these formulae and compute for the raw data and for the smooth data. So I heard some noise, some kind of, I think some video call or something's happening. It's driving me nuts. I hope some of you will complain, because if I go complain, nothing will happen. It's probably some faculty meeting. I hope you guys say that. So for that is for the first row. For the second row, I have yi plus yi plus 1 minus 2 times yi plus yi minus 1 divided by delta x squared. Are you getting these two numbers for the first and second row? For the first and second row, are you getting minus 4142? Are we getting yes, no? Yes, okay. And for the second row, are you getting again the same number? I'll make sure if I got that right or is there any mistake. Okay. If you drag it down, are you getting numbers that look similar to this? Can you confirm, please? The column highlighted here. I think it's pink, but I'm also a little colorblind, so I don't know that. Are you getting these numbers? Can you verify and tell me? Yes, you're getting good. So this is for the second derivative using raw or unsmooth data. You would do this all the way to the end, except for the last row, you would use a slightly different formula, which has yi minus 2 times I minus 1 plus this divided by delta x squared minus 77 for the last row. Are we able to get this? Yes. Sandeepan, getting this? Okay, so if some of you are able to get that, I hope others will also be able to repeat the same operation for the smooth data, except now you would do the same for the smooth data, yi plus 1 minus 2 times yi plus yi minus 1 divided by delta x squared. Okay, I'll leave this on. Kindly type this in and hit enter and tell me what you get. There's a participation exercise coming, so please try this. You are going to do most of it again for the participation exercise. Okay. Yes.
So for the last row, is it the same as from the previous?
For the last row, you use this formula, the backward formula. It involves I minus 1 and I minus 2.
So what was the value? Because I did that.
Value will be the same as the row before, minus 77 something. Okay. Are you getting 5.87? Second derivative for the second row. Thomas, yes, okay. 5.87. Okay, so I'm going to drag that all the way to the end. And for the last row, I need to do a slightly different formula. yi minus 2 times yi minus 1 plus yi minus 2 divided by delta x squared. So it should, the first and last row should be kind of the same. Yep. Okay. So again, this column here. With me so far, you calculated 2 columns of second derivative, one based on raw data, one based on smooth data. Now scroll to the right and to the bottom. Okay. Let's make sure I did the plotting right. Yeah, that is correct. Okay. Okay, please look at this. So the second derivative based on just the raw data, the noise is exploding. You can see in the y-axis values here, it's getting closer to levels like 2000 or 3000. The smooth data, the second derivative based on the smooth data isn't too much better, except the noise level is smaller, but the noise is still growing. Why is it still growing? Because even when you took smooth data and computed the first derivative, you introduce noise here. So look at where my mouse pointer is. If this were a nice sine curve or some kind of a smooth curve, that noise wouldn't propagate when you do the second derivative. But because there is noise in the first derivative, that's getting exponentially worse as you go here. So with all these pieces of information, now come back to these three ways of acquiring data. If noise minimization is your goal, which is the way to go? Should you pick a distance measurement like a GPS data? Should you pick speedometer data, or should you pick accelerometer data? Which will give you minimum noise? Accelerometer, right? Because if you get accelerometer data and you integrate once to get speed and twice to get distance, the noise will only be suppressed. The worst is if you get position data, which already comes with a lot of noise, you do the differentiation once, you get noise in the speed, and then you get further noise in the acceleration. It just makes it worse and worse. Okay. So to conclude this, okay, whenever you are doing numerical integration, you can be careless. Meaning, if there is noise in your data, nothing will happen. The integration operation will take care of it. If you have noise in your data and you are interested in doing differentiation, the noise will have to be treated first. That's what the smoothing operation was, to make it smooth. And even the smoothing operation here, if you look here, if you take this particular thing, remember we did a fit for this function, right? Let's add the fit to the data. Okay. Is it here? Yeah, right here. Okay. So I'm going to add the fit curve to that graph and tell you something here. Oh, I'm sure it's not very important. Okay. Already my fit is bad. I don't know why. Okay. So you have X and Y data to which you form a Y fit. Okay. In our case, the Y fit is A1 times a function plus A2 times another function plus A3 times another function. So from this you can get dy by dx equal to A1 f dash of x plus A2 g prime of x plus A3 h prime of x. Here is the participation exercise. Okay, this is for today. Participation. Plot dy by dx using central differencing and dy by dx through the fit on the same plot and compare. Then compute dy by dx central derivative using a second order formula, add to the plot and see if we get closer to the fit. I'll also type it up in the canvas. What I'm asking you to do is overlay the overlay. I'll remove the screen so that you can take a good picture. Okay, just hold. So overlay the dy by dx fit on this plot. So you should get a curve that approximately traces this data. Compute the compute the higher order approximation, put it on the same data and see when you approach the true value which is from the fit. Okay, it's not a exercise with a very conclusive answer, but it's to get you to compute this derivative once using the first order formula, and then second time using the second order formula, and compare it with this dy by dx fit. Again, it's participation. It's not about getting it perfectly right, but it's about trying. Try it, will give you full points. Okay. So I'll get out of the way for 1 second and let you take a picture. Okay. This is your participation. And this exercise is going to be worth 3 points. Okay. So we are doing one that was due today, that was 3 points, and then this is again 3 points due by next Tuesday. I'll put this in the email so that you have everything in writing. Okay. So to practice problems for the exam, I would suggest problems from chapter 23. So for the exam, chapter 23. Give me 1 second here. (23.9) to 23.27. Practice these problems. This is the type you can expect in the exam. What I had for the participation is what 3%. It will be tested only for the participation, but this is what you can expect for the exam. Okay. And one problem is coming. I already told you that on this topic. Okay. 8 minutes. Last lecture, I asked you about PID controllers. Did anybody look it up? What does a PID controller do? So I'm going to show you something. So if you look here, this is data, the output from a temperature sensor as part of a like a home heating system. Imagine that you left this home on a vacation, the temperature has dropped to 55. You come home and you set the thermostat to 72. This heater is trying to catch up to 72. Okay, that's the context. So if you take the timestamp and the temperature from this measured temperature, can you see this? So this is temperature versus time. Okay. So the controller, what is the controller's job? The controller does what? In a home heating system or a PID controller set to maintain a certain temperature, what's the role of the heater or the controller? it turns the system on or off, and we'll assume it has only a heater. To cool down, it just cuts off the system and lets it cool down. Okay, we can only heat, we can't cool. So this is only for some winter and not summer. So the controller decides how much power to give the heater, whether it should be 10 watts or 50 watts or whatever wattage. And how it decides that is, if you are at 55 and you are starting at T0, how much power should you give? You should give a lot of power because the initial difference is 72 minus 55. There's a lot of difference. You have to have a quick start. That is, if you, the customer, say, I want 55 to 72 should happen in like 10 minutes. What do you do for that? In your car, what is the equivalent way of saying that? What do you do in a car to get to 0 to 60 in 10 seconds? You accelerate, and that directly correlates with the engine's ability to generate thrust. Number of cylinders, volume, how much fuel, what fuel, everything. So it's related to how much propulsive force it can generate or how much acceleration it can generate. Acceleration is always a rise, right? So here you generate the power, or the controller sets the power based on the temperature difference between the set point and the current temperature. To do that, what do you need to measure? You know the set point. Set point is a number that you punch in. You don't have to measure it, but you need to measure current temperature. So the initial power heating power is proportional to T at that time minus T set. Okay. This type of heating where it's proportional to delta T, this is called proportional control. It will put more power in if the difference is high. It will put less power in if the difference becomes narrow. So as you reach 72, this delta T starts going to 0. So the proportional control will start tuning out. Okay. Then we have a thing about the rate. If you want to get there faster, how do you decide? That is, if you want the rate at which temperature changes to be, let's say, 1 degree Fahrenheit per minute or something. You want to grow at a rate of 1 degree Fahrenheit per minute. Okay. So then what you do is the power is scaled with T of T minus T set divided by delta T. Now remember this, I told you some other lecture that the days of somebody giving you a function and asking you to derivative are over. People are going to hand you data, and data might look like this. So now if you want to compute the power or make the power proportional to the derivative, this is called derivative control. And what did you learn today about derivatives? It amplifies noise. So if you don't know what you're doing when you calculate the derivative, that is you don't analyze the noise content in your raw data or the temperature data, or if you don't use a good enough difference scheme, you will end up multiplying the noise. And this has a real world consequence now. It's no longer about your exam or your participation score. This has consequence. And what will that consequence be? No, not that level of consequence, engineering consequence. If you have the derivative being very noisy, so what? One instance, the derivative is positive. One instance, the derivative is negative. And one instance, you are telling the heater to increase power. One instance, you are telling it to cut off power. What is the consequence of that to the user experience? No, not a binary answer. Tell me what exactly will happen. You are sitting in that room. That heater, instead of getting you to a set temperature, is wildly oscillating between, let's say, 80 and 65. Is that the room you want to be in? You don't want to be. And to mitigate that, you have to pay attention to the noise level in your data. There is still one more element, and I have 1 more minute. If you get to 72, you still can't just walk away. Once you get to 72, the controller still has to operate and keep the power in a certain range. And that is done proportional to the average temperature, and this is called integral control. And as you know, integration is very much tolerant of noise. So here noise is not a huge deal. But if you are using derivative control, any noise that shows up in your measurement will only get worse. So those who are serious about measurements or want to measure something and calculate something which is a derivative of that. So like you measure distance, get velocity, or measure temperature and get heating rate. If you don't understand the noise in differentiation, to put it in a very technical terms, you're screwed. Okay. All right, good. So that wraps up module 4. We got only one more left to go. Please continue to bring your laptops, do the participation exercise. We'll pick up ODEs on Thursday. Thank you.